Hello, welcome everybody. This is part 2 of thermochemistry, and what I'm going to start with today is talking about calorimetry and more specifically heat capacity. So specific heat capacity is the energy to change the temperature of 1 gram of a substance 1 degree. So we get units here of joules per gram, either degree C or Kelvin. What does that mean? Let me ask you a question first. On a very hot day, would you sit on a wood bench or a metal bench? So just picture you're in Vegas, it's wicked hot, you lost all your money, you're at the bus stop, you're wearing your shortest shorts, those super bright neon pink ones you love. There's a wood bench and a metal bench. Which one do you sit on? I think you know instinctively you sit on the wood bench, right? So you already know about specific heat capacity. We know that the metal bench is going to be hotter just from experience. Why? The reason is it has a lower specific heat capacity than the wood. So here's a snapshot of some specific heats. Aluminum is a metal here. This one has a specific heat of 0.9. So it takes, actually, based on this scale, it takes a small amount of energy relative to the others to raise the temperature of 1 gram of aluminum 1 degree. Wood, on the other hand, you need twice as much. So that's specific heat in a nutshell. Water has the highest, so it takes a lot more energy to change the temp of water, which is why when you're near large bodies of water, the weather is a little bit more temperate there. We can do something really useful with specific heat capacity. We can actually use this equation to calculate heat transfer. So anytime heat is transferred from a substance, we can measure that or calculate it using Q. So Q is heat, and we can use this equation, Q equals mc delta T. M is the mass of that substance, so it takes a different amount of heat to raise a cup of water, say 5 degrees, versus an entire ocean 5 degrees. So the mass is an important aspect of this. The specific heat, again, depending on which substance you're looking at, you'll have a specific heat for that substance. And then delta T is just the change in temperature. It's very specific. It's the final temperature, the one that you end up with, minus the starting temperature. So that's important because depending on whether one's higher or lower, you may get a negative sign here, which would give a negative sign to Q, indicating heat's released. So the delta T is a really important piece in this. Again, it's final temperature minus initial temperature. Just recall when we were talking about enthalpy change, delta H, that was also the final energy minus the initial energy. So let's just look at this with an example. You have a cup of cold water. You have 65 grams. That's the mass of the cold water, and the temperature is 10 degrees. So the T initial is 10 degrees C. It's going to warm up to 25 degrees C. So that's the final temperature. So delta T would be 25 minus 10. It warms up, so that's a positive number. In the end, what I want you to calculate is how much heat was absorbed. So let me just walk you through this. Just using the equation, Q equals MCAT, MC delta T. You plug in M, 65 grams. You plug in C, which would be given to you, or you can look at the chart. That's 4.184. And write all the units so you could track and see that in the end you'll end up with joules. And then T final, 25 minus T initial. Crunch the numbers, you get 4080. And this is out to 2 sig figs. So your final answer is 4,100 joules. So notice that this is a positive number. Overall, that water needed to absorb heat. And just ask yourself at the end, does that make sense? It went from something colder to warmer. Yes, it did need to absorb heat. For example, you put ice outside, you put a cup of cold water outside in the sun, it absorbs heat from the sun to warm up. Okay, this leads us into calorimetry. This is a method that chemists use to measure heat transfer. So When we want to really look at how much energy is, say, released or absorbed from a system, we need a way to calculate that experimentally. So what we do is we basically use the first law of thermodynamics and we measure the surroundings. We know the heat transferred to or from a system is the exact same heat absorbed or released from the surroundings, but with the opposite sign. So just visually, if you have a system here, pink, one that's endothermic, it absorbed heat from the surroundings. Conversely, if you have a system that's exothermic, it releases heat to the surroundings. So what we do with calorimetry is we measure the surroundings. If we notice a temperature increase of the surroundings, that means that heat was absorbed from somewhere, it was absorbed from the system. So that means the system itself released heat to the surroundings and increased the temperature of the surroundings. One of the things that we use to do this, a really crude but effective way to do this, is with a coffee cup. So this is my Starbucks calorimeter. And basically you have an insulated system. Here I have two styrofoam cups. I have a cork on top. I have a thermometer to measure the temperature change, delta T. And then I have a stirrer just to mix things up, make sure everything's equilibrated. I have a body of water in here. That is actually my surroundings. The sample that I'm going to look at could possibly be a block of metal. That's your system. Alternatively, I could have had a salt dissolve in here, or maybe I could have added an acid and base. And basically the chemicals, those would have been the system, but still the big body of water is your surroundings. So let's just do a classic calorimetry problem. This is going to be heat from a solid. So I'm going to, in this example, I'll have a hot solid going dropped into the water, and the heat from the solid is going to be released to the water. And we can measure that. So again, first law of thermodynamics says that the heat from the system, our case, the solid, is the equal and opposite sign of the heat of the water. Q of the solid equals minus Q of the water. Don't worry about who's releasing heat, who's gaining heat, where the negative sign is. The key is that you just have one negative sign here. Mathematically, you could put it on this side or this side, it doesn't matter, but you need one negative sign. Let delta T do the rest of the work. As long as you're correctly inputting T final and T initial, those numbers, that'll give you the correct signs, and overall you'll have the correct sign if you ever need to determine endo or exothermic. So basically, I have Q solid equals minus Q water. I expand that because I know that Q equals MCAT. So I could say Q equals M of the solid times C of the solid times delta T of the solid. And that also equals minus MC delta T of the water. Okay, so that's the equation that we'll be using to solve a problem on the next slide. But let me just have you consider a couple things. If the object is warmer than the water, what direction does the heat flow? So if you're the object, if you're the solid, you're the system. If you're hotter than the water, I told you energy from a hot body flows to the cooler body. That means energy will be released to the water. So the answer to this question is the heat flows from the system to the surroundings. If you had an object that's cooler than the water, then the heat from the water will then flow towards and to that object. One key point, they all come to the same identical equilibrium temperature. So that's the key to solving these problems. They all have the same T final. So in this case, in the lower case, if an object that's colder than water is dropped in here, then the heat or energy is transferred from the surroundings to the system in that case. So from the perspective of the system, it's an endothermic process. For the top one, from the perspective of the system, it's an exothermic process. Okay, so let's do this problem. You have a cube of gold that's heated up at 163 degrees C, and it's placed in a calorimeter, just like the coffee cup one I showed you. This calorimeter contains 60 grams of water. What's observed is the temperature increases from 19 to 20 degrees C. The question, what is the mass of the gold? So I give you specific heats of gold and water. You can use the equation, understand that they both come to the same equilibrium temperature, and you could solve this problem. So pause this and try this problem on your own, and then I'm going to go over it. Okay, so again, the key is to know that the heat given off by the gold is the same heat, the opposite sign of the heat absorbed by the water. So you equate the MCATs, but have one minus sign in here. Also, they come to the same equilibrium temperature. So M of gold is an unknown that we're trying to solve for. I just plug in the specific heat of the gold, and then T final for both is 20 degrees. Because the water goes to 20 degrees in the end, that means both of them do. So for the gold part, T final minus T initial is 20 minus 163. Then go to the other side, minus MC delta T for the water. You plug in 60 grams for the water specific heat, and now it's 20 minus 19. Crunch the numbers, you get a mass of 13.5, and your final answer is 14. Even though everything looks like it's out to 3 decimal places, there are only 3 sig figs. There are only 2 sig figs in the answer, because here when you do the subtraction, 20.0 minus 19.0, you get 1.0, which is 2 sig figs, and that limits the final answer. Okay, one other problem. This involves mixing hot water and cold water. So you have 120 grams of hot water, and it's added to cold water. So the hot water's at 95, the cold's at 15, but they both come to 35 degrees C. My question is, what is the mass of cool water? So this is useful if, say, you want to find out how much cold water do you need to add to get the temperature, total temperature, to certain degrees. So how do you do this problem? Take a moment just to think about that for yourself. Obviously, you need to relate this to the first law of thermodynamics. The heat given off by the hot water is equal and opposite the heat of the cool water. And then you can equate the MCATs. So that's what I'm going to do. The MCAT of the hot water is equal to minus the MCAT of the cold water. Since the specific heats of the waters are going to be identical, I just cancel those out. If you want to input that same number, that's fine. It's not a problem. I just simplified it. Then just plug in the numbers. The mass of the hot is 120. The temperature final is 35 minus 95 minus the initial, and then just continue. It equals M cold, which is what you're solving for. And then the final temperature of the cold is also 35 minus its initial temperature. You get 360 grams in the end. Okay, so this is where I want to end here. Make sure you're reviewing both parts of this and practicing problems. All right, I will check in with you guys later.